All right, so now that we've explored finite geometric series, whenever you hear the word finite, probably the other word that immediately comes to mind is infinite. And something that's infinite, it never comes to an end. So before we talk about that, I want to mention a very interesting, what's called a paradox. And a paradox is something that seems to be true and false at the same time. So one of the most famous examples is if you had a time machine, could you go back in time and make it so that your grandparents never met, let's say? And it seems like you could if you somehow could time travel, but on the other hand, you can't because if you made it so that your grandparents never met, then you would never exist to go back in time. So that's kind of what a paradox is. It's a little bit confusing like that. So in that case, what is Zeno's paradox? Zeno's paradox, it was formulated by a Greek philosopher named Zeno, and here's the idea. And there's kind of a cartoon right here. This is coming from um, it's a website called xkcd.com. It's kind of like a math science website, and they have some humorous cartoons there. So in any event, Zeno's paradox. Zeno is a Greek philosopher, and he said the following. There's kind of uh, a terrible artist here, so please excuse my cartoon in advance. But let's say you have somebody right here, and there's a destination. Let's say there's like a wall right here that they want to reach, and let's say the wall is 2 yards away from them. 2 yards. Well, Zeno's paradox goes like this. Zeno is trying to prove that motion of any kind is impossible. So his answer to this question is no. You can never actually move. All change is impossible. It's obviously very counterintuitive. We seem to see things changing around us all the time. How could change be impossible? Well, here's his argument. See if it convinces you. He said, if I want to travel 2 yards, if I want to get to this wall right here, it makes sense that first I would have to go halfway. Okay, so I'd first have to travel a distance of 1 yard. Okay, that makes sense. That seems reasonable. You can't go 2 yards unless you first go 1 yard. So he says, okay, now I'm halfway away. Well, now I'm 1 yard away from the wall. So I'd have to go another halfway. So that's a half a yard. Well, now I'm a half a yard away from the wall. I'd have to go a quarter of a yard to get there. And now I am a quarter of a yard away. So I have to go half of that. I have to go an eighth. And now I'm an eighth of a yard away. I'd have to go half of that, which is a 16th. And his point is you would be eventually standing right here, like millimeters or micrometers away from the wall, but you're never going to reach the wall. You're never going to get there because before you can get there, you'll have to go halfway. So you'll be going a billionth of an inch, let's say, and then you'll have to go 1 2 billionth. I mean you'll keep dividing into smaller and smaller fractions, but you'll never reach. And he actually goes further. He says, remember this part at the beginning where we said we were going to go a yard? He said even that's not possible because before you can go a yard, you'd have to go half a yard. Before you go half a yard, you have to go a quarter. Before you go a quarter, you have to go an eighth or 16th or 32. So you can never actually take your first step because you first have to take half a step. So that's what this cartoon is saying. It's kind of in accord. He says, my client couldn't have killed anyone with this arrow and I can prove it. He's going to try to prove that you can't shoot an arrow at all because it would never get there. It first has to go halfway. And so apparently the attorney is saying, or the judge is saying, I'd like to examine your proof, Zeno. You may approach the bench. And Zeno, of course, says, well, I can never reach the bench. So Zeno's paradox. Now, Aristotle, the Greek philosopher, had an answer to this from a philosophical standpoint. It's based on something called actuality and potentiality. And there's another answer to this based on calculus. But the main thing you're doing here is you're actually summing up an infinite series. You're summing 1 plus a half plus a fourth plus an eighth, and you're doing this forever. Okay, and if you could, in theory, add this forever, here's what would happen. Okay, and we'll talk about this in just a sec because our topic is infinite geometric series. So I'm going to talk about something called divergence and convergence. But here's what would happen. If you add these, you have 1.5. If you add this onto it, you have 1.75. If you add this onto it, you get 1.875. Okay, if you add this onto it, I believe you get 1.937.5. I'm not sure. I don't have a calculator. But this looks like it's getting closer and closer to what? And the answer is it's getting closer to 2. That's the sum of this series right here. I'm going to show you how to find sums. Before we do that, though, let's talk about what these words mean here. Divergence and convergence. Okay? If a series diverges, and whether something can be added or not, because you can't add all infinite series. You can only add series where r, which means our common ratio, where the absolute value of r is less than 1. That's what this says right here. Absolute value of r is less than 1. So in that series we just did, 1 plus a half plus a fourth plus an eighth, what is r right here? What are you multiplying by each time? And the answer is you're taking a half each time. Since 1/2 is less than 1, you can add that series together. If the absolute value is not less than 1, if it's greater than or equal to 1, okay, if it's greater than or equal to 1, that series is going to diverge. You're not going to be able to add it together. Okay. So in this case, what we want to do is just simply look at these three series and tell in each case whether it converges or diverges. And that's easy to do. The only thing we have to look at is this number. We just have to look at r. So right here, r is 1/3. That means it's less than 1/2, or sorry, less than 1. So therefore, this series will converge. That's all we have to look at. Right here, what's the common ratio? Well, that's not as obvious. So in order to find it, what we'll want to do, erase this for a sec. What we'll want to do here is actually find the common ratio how we've done it when it's not obvious. And the way that we do that is take each number and divide it by the term right before. So we'll divide that by 4.6, and if it is a common ratio, which it should be, then we should end up getting the same thing each time. Okay, and what does this turn out to be right here? Let me just plug that in a calculator real quick. So 4.14 divided by 4.6, like 0.9, I believe. Yes, 0.9 is the answer. So this is 0.9. That means this is 0.9 also. And that fits our rule. Remember, our rule is that it has to be less than 1. 0.9 is less than 1, so this is going to converge. We will be able to add that series together. Okay, number 3, the last one, this is the common ratio. Okay, that's sigma notation. Remember, common ratio is what's being raised to the power. R is equal to 2.5, and 2.5 does not meet this condition. So this means that we would not be able to add that series together. That's going to diverge. In the next video, we'll talk about how to actually add infinite series.